Okay, so we'll begin with an experiment on half-wave rectifier. Then we'll go over the application of voltage limiter. So we'll talk about a little bit of theory. We've seen an example of this in the last class. So we'll talk about an experiment. Then we will go into light generation and detection using LEDs and phototransistors. And the last thing that is on the agenda, and the last thing for experiment 8 is Zener diodes. So how we can use a Zener diode to get voltage regulation. So this is light applications. This is voltage regulation application, and this is just a limiter application. Um, So that's the goal. We don't have to complete all these items because we still have a class on Monday. Oh, sorry, class on Thursday to finish whatever remains today. So we'll see how we go today. So if I go back to where we stopped in the previous lecture, we were using a half-wave rectifier to convert an AC current to a DC current, meaning something that changes with time as indicated by the black line over here, to an output voltage that does not change with time. So ideally you would want something to stay more or less the same. That would be your ideal output. However, to go from here to there, it's not one step, one easy step. You have to do it in a few steps. So the first thing that you can do is start with using a half wave rectifier, for example, to at least go from a signal that has a zero average to something that is positive average. And we can do that by using simple one diode. And then if we are able to connect a capacitor across this resistor, what we can do is we can charge and discharge the capacitor based on a positive cycle and then energy going down. So by that, we will have something that looks something like that being measured across the capacitor. And because it is smoothing out the output voltage, it's called a smoothing capacitor. And the effectiveness of the smoothing capacitor and also your half-wave rectifier can be measured by you measuring the ripple voltage, which is essentially the range of voltages over which the output is going to vary. So we want that ripple voltage to be as small as possible so it looks like a DC output. So that's what we talked about the last class, and we talked about the impact of using a big versus a small smoothing capacitor. So obviously, if we start off with say a standard 4.7 microfarad capacitor, you might be looking at a blue line, the green line there. So it charges up and then it discharges based on the time constant established by R2 and whatever the capacitor is. Then it charges again and discharges and so on. But if we have a big capacitor there and a small capacitor there, then the rate of discharge is going to vary, which means my ripple voltage is going to increase or decrease. So for example, if I have a smaller capacitor compared to 4.7 micro, say for example, if I have a 1 microfarad capacitor there, it's going to discharge faster because it's a smaller capacitor, which will increase the ripple voltage, and vice versa for the big capacitor. If I go to a 10 microfarad capacitor, it's going to take longer to charge up completely. Discharge completely. So it's going to stay high, so stay at a higher voltage for a longer time, thereby decreasing the ripple voltage. So that's where we were. Today I'm going to a slight difference from how we have been doing lectures earlier to today is going to be because there are so many experiments and so many little topics. So I'm going to switch back and forth between discussing the concept or the application and how the circuit elements are able to do that, and then I'll switch back to experiment and I'll come back to a discussion. So it'll be It will not be a clean separation between discussion and experiment. Um, so let's see. Let's start with the experiment here. The experiment is of a half wave rectifier. So a half wave rectifier is going to give us, if the black line is an input, it is going to give us a red line at the output. And that red line, note that it is being measured across the resistor. If this guy is the source. If you measure across the resistor, you should see the red line. And of course, if you subtract the two, that will be the voltage across the diode D2 over here, which we are not interested in for half wave rectifier. We might be interested in that if we were doing a voltage limiter. So let's start with the experiment here. I am going to quickly set up my board and start waveforms. The experiment I'm going to work on is, let's see if I'm going to erase this capacitor thing here and show you what the experiment should look like. So wave gen from my analog discovery should go into a diode, into the anode, the positive terminal of the diode 4148. So it's still a small signal diode there. The cathode is connected to a 10K resistor to ground. I'm measuring my input signal, for example, the source on channel 1, and I'm measuring the output on channel 2, which is the resistor. So I'm going to expect a plot which looks like this if my signal was my signal was a sinusoidal. But I think I need to use a triangle wave with a 1 kilohertz frequency and 5 volt amplitude for this. So things will change to a triangle wave, and that should be it. Um, One key thing that I would like to say is at the peak, the difference between these two guys should be about zero point 0.7 volts. The reason is it's going to take about 0.7 volts for the diode to turn on. So that's the threshold for the diode D2, which is going to be at the peak, the difference between the two. So let's see. I will build this circuit and we will go through the experiment. All right, let's see. Should be okay. And this should do it. So I've got my board here. I don't need a 1 kilo ohm resistor. I'm going to simply use a diode and a 10 kilo ohm resistor. So I've got a 10 kilo ohm resistor right there. I've got a diode here. Not too many things involved in this experiment, which is why we can do this on the fly. Um, so I'm going to connect my yellow wire now to the positive end of the diode right there, followed by 1 plus, and this is a differential voltage. So uh, one end of orange goes to the cathode of sorry, not the diode. This is going to go at this end, and it is also grounded, so I can essentially do this, followed by so ground there. Let's see. Orange needs to go measurement at wave gen, so that's going to be on yellow. Then I have the second channel across the resistor R2, so blue stripe is going to go to ground again, and blue is going to go across to the junction between the diode and the resistor. So I've got wave gen, I've got the two components in my circuit, I'm missing ground, that's it. So I'm going to take a black wire here and connect it to ground right there. I believe that completes all the connections. Not too many, and if you look at all the other circuits that we have been building, this is quite straightforward. So I hope that you are able to quickly relate this to the schematic that is shown on the screen as well. So nothing too fancy here. So let me now start waveforms so that we can measure things. Okay. Okay, so my circuit board has been detected. Let's see, do I need a scope? Yes, I do. I also need my wave gen, and I don't need anything else. I just need wave gen and scope. So let's see if I can bring this. Well, I can make this my entire window. I had to choose a triangle wave with a frequency of 1 kilohertz and an amplitude of 5 volts. So I've got that set up over here in for my wave gen. So that's ready to go. I'll go into scope and I'm measuring both channel 1 and channel 2. Right now my base is 1 milliseconds per division. If a frequency of 1 kilohertz is being measured, which means the time period is 1 millisecond, in order to see two time periods, I would take a look at 2 milliseconds divided in 10 divisions. So that's 200 microseconds per division to be set at the base. I can set the ranges of channel 1 and channel 2 to be 2 volts each per division, and I'll adjust later. So I'm going to start wave gen first, then start scope. And as you can see, I have a half wave rectified output. This, however, does not include the smoothing capacitor. It is just simply a diode and resistor. There's no capacitor right now. We are going to add that later on. I can increase the plot width to 3, so hopefully you can see that better. I can remove the noise here on both channels. So that should be it. So on the orange line, we have the wave gen. It's going up and down. It's going 5 volts up. So plus and minus 5 is the voltage range on the triangle wave in a frequency of 1 kilohertz. And the blue voltage output is being measured across the 10 kilo ohm resistor. And as I mentioned, the difference between those lines is going to be on the y-axis. It's going to be 0.7 volts, which is the turn-on voltage or the threshold voltage for the diode. But as simple as that. There's nothing too fancy happening. The circuit should be straightforward for you to relate to the circuit diagram, and the outputs are in agreement with the theory that we discussed. So what I'm going to do is I'm going to take a moment here and see if you have any questions about half wave rectifier. Right now, without the smoothing capacitor. All right, looks like you guys are okay with this. Um, so in the write-up, it says you can either use analog discovery to generate your plot, so just this, or we can also use MATLAB to sketch this out. So by doing a export data and then um, doing it in MATLAB. So just for fun, let us see if I can do this. I'm going to try to see if I can make a quick poll and ask you a question. The question is, do you want it to be analog discovery plot or plot using waveforms? Uh, Figure this is what B1. Okay, and then I'll say the answers are waveforms and MATLAB. I'm not even going to include Excel in this. I'm just trying this out. Let's see if I'm not recording your individual responses, as you can see. So I'm just going to see if this works, and I hope all of you participate. Let's see, open da, da, da. I think if I say open poll, you guys should be able to see this. Okay, so on your end you should see, all right, so I'm seeing people answer. So let's give it a couple minutes and see how this goes. This is brilliant. All right, so we got 3 left. I think if some of you are TAs, I don't know if you answered or not, but um, I'm really happy with how this turned out. It was quick and easy, and clearly there is one winner. So if I click on bar graph, can I see this? Oh, okay, it's right here. So it looks like waveforms got. I can close the poll now. Take a look. So there are 20 seconds if anybody wants to uh, probably fill in last minute entry, or I should say last second entry. Okay. So 22 people responded. with 14 votes going for waveforms and 8 votes going for MATLAB. So I think I know my answer. Brilliant. And just so that I have this for future, I'm going to save it as well. All right. Thank you for participating. This helps a lot. Okay. So I'm going to use waveforms. I've already generated this. However, later on, I want to add some text to this plot. I want to add some key data points, and I will share this with you on Piazza as usual. Okay, so let's move on. What is the next thing on the agenda? Sorry, not on the agenda, on the experiment list. So we have done this, produced a plot on oscilloscope. We measured channels 1 and 2, blah, blah, blah. We also talked about who wants which software. So we looked at that. Let's move on. The next slide is a discussion on full wave rectifier, which we completed in the previous lecture. There is no PSpice or the experiment circuit building component over here. Page number 11 has things that are related to a half wave rectifier with a smoothing capacitor. So you start with without a smoothing capacitor, then you add a smoothing capacitor. But all of this on page number 11 is a PSpice simulation that is highlighted in yellow. So I hope that you guys will do this. Then in figure B-6, it is also a capture PSpice simulation. But in this case, we add a 4.7 microfarad capacitor C1. So you can explore that in Capture PSpice software. On the next page, page number 12, all of this page is going to be the hardware implementation of the rectifier, highlighted in blue. So for this guy, figure B-7 is what we already did just now. We did that. We measured things. Over here it is saying use the waveform generator to supply an input sinusoidal. The frequency is 100 hertz. Um, we did it for 1 kilohertz. That's fine. I can provide both of them, both those results. But it's not going to be of any, things are not going to be different in terms of how they look. It's just going to be the time window for which we observe them. But we did this already, 100 hertz, sorry, 1 kilohertz. So actually, let me do that. Change it to 100 hertz, see what happens. Nothing should change dramatically as far as the without the smoothing capacitor is concerned. So I just did that, and if I look back here now, because I changed my frequency, I'm also going to have to adjust my time scale. So I changed that by 10 times. And this is going to be useful to do right now because we are charging and discharging a capacitor, so that the time matters now. So I changed the frequency. In figure B-8, I'm simply going to add a capacitor C2 in parallel with R2. So I'll bring my capacitor in. I have it right here. It is, yes, it is a 4.7 microfarad capacitor. So I'm going to simply add this in parallel with so let me stop wave gen, add the capacitor in parallel. I hope you can see that. And then if I turn this on, this should be, and as you can see, it charges up and then it slowly discharges, charges up and slowly discharges. So it is a half wave rectifier with a smoothing capacitor of value 4.7 microfarad capacitor, 4.7 micro. We can actually look at more times just so you can see the this is probably not a good one. We were at 2 milliseconds per division. So if you can see this, and if I were to highlight only channel 2, and if I were to make the range a little bit um, different, okay, no, not this. I want to make it on the other side. And I hope now you can see that things are pretty much flat, and they are flat around that 4 volts region, just below 4. So the average of the signal has gone up from 0 to about 4 volts, and it is over time remaining constant. Not very constant, it is changing, so there is a ripple voltage there. However, it remains the same, more or less, with a half wave rectifier. So let me come back now to an offset of 0, and then make this 2 volts per division, and also turn this on, and then go back to my original setting of 2 milliseconds per division. Okay, so that's my half wave rectifier with a smoothing capacitor. The value chosen is 4.7 micro. Again, we need to take these, and we need to take that data from channel 1 and channel 2, and again provide a plot in waveforms and include that in your report. So again, I will add text to that plot and give it to you using Piazza so that you can use it in your report. And you will have to add a few things. So for example, if you see this point here, it says use the cursors to read 5 voltages and times, including the minimum and maximum voltages and 3 other points. So you're essentially trying to compare the plots that you generate with PSpice and the plot that we generated in waveforms. So you are going to add some points that you obtained experimentally to your PSpice plot, so that you have a good comparison. So I've highlighted that point here. Add the experimentally measured points to the plot generated with PSpice. You had generated that PSpice plot on the previous page. That was with the smoothing capacitor that we highlighted in yellow. So essentially 5 points, 2 of them are minimum and maximum, that will indicate the ripple voltage essentially, and then 3 other points in the middle. I will choose them arbitrarily and then place them on the graph. And then once I share that with you, you can add those specific data points to your PSpice plot to see how far your PSpice results are from the experimentally obtained data. Let's see. Now, at the very end, we are asked to vary the frequency of the function generator and observe both the input and the output voltage of the rectifier with the capacitor. And we can also connect a capacitor of say 100 microfarad capacitor value to see the effect. So first I'll start with the 100 microfarad capacitor. So I'm going to change it, and I hope that things will get even better as far as the rectification is concerned. So I've got a 100 microfarad capacitor there. I'm going to go back to my waveforms window. I'm going to turn off wavegen, and I'm going to pull out my capacitor from here. I'm going to put a new one in there, a 100 microfarad capacitor, And once I do that, all right, I added a 100 microfarad capacitor, and I'm going to change the scope now, add wave. So now, as you can see, things have become pretty much flat. There's very little ripple if we compare this to the previous one. So that is essentially an indication that we are able to use a higher capacitor value, such as a 100 microfarad capacitor, to smooth things out even better. So let me stop this and change the frequency. So let's see if I change the frequency here. Um, Say this was 100 hertz. We already talked about what happens when we change the capacitor. We demonstrated that. Let me stop wave gen, remove the capacitor, put the old one back so that we can see the effect of changing the frequency. So I'm putting the old capacitor back here, and I'm going to go back to wave gen, take a look at this. So this is going back to the old one. That's the ripple that I have now. And if I were to change the frequency, what is going to happen? Well, the yellow lines will be closer. So the peaks will be closer to each other if I increase the frequency, which means my capacitor will not be allowed to discharge to a lower value, which will result in a smaller ripple voltage because I'm stopping it right here or right here, right? So it'll only discharge for a smaller amount of time, which means the change in voltage going down will not be too big, leading to a smaller ripple voltage. And we can talk about that and see. Let's see what happens. 100 hertz, I'm going to increase that to 1 kilohertz, go back to scope and change this to 200 microseconds, for example. And if you see this, it's the same scaling, but if you see this, things have become a lot more smoother uh, because I did not change my y-axis at all. So we are observing a smaller ripple voltage if I increased the frequency of wavegen. Now, if I decrease the frequency of wavegen, let me see, I was at 100 hertz. If I go down to 10 hertz, the other extreme, and go back to scope, and now I'm going to have to adjust my uh, scale. So right now I have, hold on, this was at 200 microseconds per division. This is going at 10 hertz. So I need a higher one, 220. Okay, so that's it. So now, as you can see, when I decreased the frequency, my ripple voltage has increased. Again, I've not changed the y-axis here. Now, essentially that happened because the peaks are coming in uh, slower. So the capacitor is being allowed to discharge for a longer time. And in fact, you can see the exponential discharge very clearly over here. Um, Earlier, that was almost linear because we were stopping it right there. Um, so I hope you are able to see the effect of changing the frequency of wavegen on the performance of rectification. So if you reduce the frequency, your rectifier does a poor job. If you increase the frequency of wavegen, your rectifier does a better job of converting AC to DC. However, in most applications, you will not have the choice of changing the frequency of the wavegen, but you will have control over the circuit elements. So changing the capacitor from 4.7 microfarad to a bigger value, so 47 microfarad, for example, will do the trick. So that's another way of improving the rectifier. Okay, so let me stop WaveGen. Let me stop the scope as well. Let me go back here and so we varied the frequency of WaveGen. We observed both input and output. Sure. We tried to connect a bigger capacitor. Yes, we did all of this. Let's move on. Now on the next page, this is page 13. Yes, it is page 13 of the experiment write-up. We start talking about voltage limitation. So voltage limitation is essentially, let me talk about that here. Let's say, right. So if you think about voltage limiter, the goal is to limit the maximum and minimum value of a signal. So for example, if we have say a sinusoidal wave and my goal is to limit the input to a certain system. So suppose I have a block here and it takes an input and it does something to that input and then it gives out an output. Over here I have a system. There's the input here. So in most systems, you will have to deal with acceptable voltage range for the input side. We cannot overwhelm the system with a very, very large input. So because there is a requirement on the voltage range here, we will have to use either we can do this in many ways. We can actually squeeze this down, and there are ways to do that. But we can also literally chop this off. So for example, we can say, all right, let us make our limiter function for, maybe plus and minus 2 volts. Beyond that, whatever is there, I'm going to literally chop it off. So that's called a hard clipping. That application is a hard clipping, because when we do this, we are essentially losing information because we are chopping it off. So if we do that, what is going to happen? The output, let's say I plot the output in red, is essentially going to look like the input only until it reaches that point. But if it reaches that point, it is going to flatten out there. So that's going to get limited over there. And then it's going to come back. Over here is all fine. Over there it's going to get flattened out. And then beyond this, it will get flattened out. So that's how we are getting that voltage limiter. So the output never crosses uh, the limiting voltages. And now we can give this to the input. So the actual input comes in, goes through this voltage limiter, which we can design using diodes, and we can go into the system. So that's a very quick discussion on why we would want to use a voltage limiter. And we talk about that in a little bit more detail by doing a hardware implementation of this limiter. So in this case, you have a resistor R1, we have two diodes, and as you can see, they are both pointing in opposite directions. So D1 is going to be forward biased. Let's see if I can draw like a wave gen. So what I'm going to do is I'm going to say this is my wave gen. Let's say I have a positive half cycle, negative half cycle, positive half cycle, and so on. I'm using a sinusoidal wave here. So if I highlight my positive cycle in yellow and my negative half cycle on the input in blue, what is happening to the diodes? Well, I can say that the D1, this particular diode here, is forward biased. In other words, it allows current to pass through it when we are operating in this yellow region, because that's when the positive voltages are coming in. So that D1 is forward biased in that case. At that time, D2 is reverse biased, so it's not going to allow any current at that time. Now, in the other case where we have negative half cycle on the wave gen, we are essentially going to have D2 forward biased. So that guy will be allowing current to pass through in this region when the wave gen is in this region, negative voltages. But at that same time, D1 will be open circuit. So that will not allow current to pass through it. So as you can see, it is allowing both positive and negative voltages to go through. So there is current flowing through. However, they are both get limited to the threshold value of the diodes, because we are measuring a voltage on channel 2, which is essentially the voltage across the diodes here. We will have limited both of them. Let me try a little bit thicker here. Limit will be here, and then because of the blue guy, the limit will be there. And those values essentially will be, let's see, 0.7 volts on both sides. Because beyond that, the voltage of the diode doesn't go beyond that. It will get limited to that point. So it will follow the input between those two lines, but it will never cross those two lines. Okay, so let's explore that using an experiment. Over here we have, we are going to set up this figure B-10. Let's do this relatively quickly. So let me remove my smoothing capacitor. Don't need that here. I need two diodes. I have one for now. I need wave gen, so I have wave gen coming in. I'm going to remove my diode. I'm going to remove this 10 kilo ohm resistor. Don't need that. I need a 1 kilo ohm resistor, so I bring in my brown, black, red resistor, and that is between yellow wave gen and another point. I'm not interested in measuring voltage across R1, so I'm going to remove that blue channel from there. Actually, that has to go there. Because I need to measure the voltage across the ground here. I'm going to put one diode facing down. So positive goes up top, negative goes to the ground, like that. And then I'm going to bring in another diode to connect it in the reverse direction. So I'm going to try to quickly find that. Alright, I hope I have the right diode, 4148. Yes, it is. So now this is going to be in the reverse direction. So the black ring, which indicates negative, the cathode, is going to be facing up for now. And I will place this exactly between the same 2 points. But I'm going to bend the leads a little bit so that you can see that clearly. Right, so I've connected that to the same points, the same end points, but I've bent the end terminals so that you can see them separately. One is pointing down, one is pointing up. Okay, blue is measuring across the diodes, yes, and I need wavegen to be measuring the source, which it is right now. So everything is set up properly. It's exactly the same way as it is in the circuit diagram, figure B-10. So let's go back, look at wavegen. Oh, sorry. Let me look at what so the function generator is a sinusoidal input, 5 volts amplitude, 100 hertz frequency. Okay. So wave gen, 100 hertz is the frequency, sinusoidal wave, 5 volts is the amplitude, sure. Run wave gen, go back to scope, run scope. I don't need that much because I have 100 hertz. Let's see, 2 milliseconds per division should do it. And we can clearly see that the output voltage is getting limited to uh, so if I just zoom in on channel 2, uh, make it 1 volt per division, you can see that around 0.7 volts it gets limited to that value. They appear they are appearing on a different scale here, which is why, well, let me do this as well then. All right, so now you can see both the input and the output. The output is getting limited to plus and minus 0.7 volts. The input, however, is going from plus and minus 5 volts. They're both sinusoids. The middle one is essentially clipped off beyond 0.7 on the both the positive and the negative side. So that's your voltage limiter. Um, and we can do fun things with this. We can have 2 diodes facing down, 3 diodes facing up. So we can so that we have different limiting voltages on the positive side and the negative side. And when we were talking about this in the last class, I think we did an example that was similar to that. Okay, so that's your voltage limiter, and let's see what is expected out of us for this one. So again, take an analog discovery picture of this circuit. Sure, I will do that after I add text to the plot. Record at least 5 experimental voltages and add them to the PSpice output. So this is very similar to what we discussed earlier. So I will add 5 experimental voltages on the plot that I provide to you, and you can take that data and uh, import it to your PSpice plots. Then we have some questions. What is the effect of altering the amplitude of your circuit? So now we are asked to repeat the measurements with 100 hertz, same frequency, but 2 volts sinusoidal input. So if I go back to wave gen, make that voltage to 2 volts, what is that going to affect? Well, the input went down. However, the output is still getting clipped between plus and minus 0.7 volts. So in terms of uh, information, I'm losing less because earlier I was losing everything beyond 0.7 all the way to plus and minus 5. Now I'm losing less information because I've sort of compressed my signal uh, to plus and minus 2. Let's see, what else do we have in terms of um, Alright, take an analog picture, 2 volts, sure, I will do that. The next question is alter the circuit to limit the voltage only in one direction. Okay, so this is interesting and a little bit different. Um, how can I limit it only in one direction? Well, we can do that by essentially removing one of the diodes, and it doesn't really matter which one. So suppose I wanted to limit it only in the positive direction, like for example over here. I wanted only to limit in the positive direction. In that case, because D1 is responsible to establish that positive uh, limiting, if I remove D2, the diode that is pointing up with the negative terminal pointing up, I will be only limiting in the positive direction. So let's try that. I'm going to show you this. Go back to my original wave gen. Let's see. Go back to original wave gen with 5 volts. Come back here, and then I'm going to go to my circuit and pull out the diode that points up, meaning the negative is up. So if I remove that out, you can see that it is getting limited only in the positive direction, and during the negative cycle it follows the input. So the limiting is only in the positive direction over here. So that's how we answer that. And we are also asked to so yeah, remove one of the diodes. We did. What part of the signal is being limited? The positive half cycle
of the input is being limited in that case because we removed D2. And now we can reverse the polarity of the diode that remains. So essentially we have D1 that is left into our circuit. We can reverse the polarity of D1 and we can talk about what part of the signal is going to be limited next. Well, if we reverse it, that is essentially going to be like D2 was originally there and D1 was removed. So it's going to limit the negative voltages in that case. And we can observe that by going to this plot and removing D1, flipping it, putting it back in. And if I do that, you can see that the limiting is now on the negative side. So the negative half cycles are being limited to negative 0.7. The positive cycles are following the input. There's a question online: is there a physical voltage maximum before the diode burns out? So the physical limitation on this is primarily going to be on the negative side for the diodes, but on the positive side, it is going to depend on the other elements. So for example, if you look at this, let me talk about the, uh, where is that? Right here. So as you can see, the IV characteristic of the diode, on the positive side, the voltage cannot across the diode cannot go above 0.7, which means that if you keep on increasing the input voltage, the diode can only take in around 0.7, which means that the remaining voltage will be going across the resistor R1. So as you're increasing that voltage, that resistor R1 will get more and more current across it. So essentially we will be going up in terms of our, uh, in this region we will keep going up. So that means that we are essentially increasing the amount of current that flows through that resistor as we increase that input voltage. Well, the resistors are going to be, in our lab we use quarter watts, 0.25 watts as the rating for the resistors. So they will burn out if the current through those resistors exceeds that value, and that value can be calculated by using, power equals V times I. V is IR, so power is I squared R. So given the value of power to be 1/4 of a watt and given the value of the resistor to be 1K, we can find out the maximum current that should be allowed through that resistor R1. So the other parts of the circuit will establish the maximum voltage across the diode. The diode itself will not. All right. I hope that answered your question, Justin. So let's see. Where were we? We were talking about. Let's see. We did smoothing. We did. Yes, we did that. We just did all of this rectifying stuff. Um, I'm going to take a quick look at the time here. So right now it is 8:56. Let us take a quick break. So I will stop recording